All right, today we're going to tackle a word that can make a lot of people nervous: calculus. But hey, forget the scary formulas for a second. At its core, calculus isn't just a bunch of math problems. It's actually an amazing story. It's about human creativity, about finally solving puzzles that people have been stuck on for centuries. So let's just dive right in.
So let me start with a question that, sounds a bit like a riddle. What on earth does the exact speed of a falling rock at one instant have to do with finding the area of some weird, curvy shape? They seem totally unrelated, right? Well, the answer is one of the most powerful ideas in all of science.
So here's our roadmap. We're going to start with two really old puzzles, the tangent problem and the area problem. Then we'll see how one single, brilliant idea, the limit, cracks them both. And at the end, we'll see why this all still matters so much today.
You see, calculus didn't just appear out of thin air. It was born out of necessity, forged to solve some really practical, real-world problems. There were these two big questions that just kept stumping the greatest minds for ages, and they basically set the stage for a whole new kind of math.
So on one hand, you've got the tangent problem. How do you figure out the steepness, the rate of change at one single tiny point on a curve? And on the other hand, the area problem. How do you find the perfect, exact area of a shape that has a curvy side? Like I said, they seem like they come from different universes, but there's a hidden link between them that changes everything.
Let's dig into that first big question, the tangent problem. This is all about trying to measure change in a world where, let's be honest, things are constantly changing and almost never move in a perfectly straight line.
I mean, think about a straight line, like a perfect ramp. Finding its rate of change is a piece of cake. It's just the slope, right? Rise over run. And that slope never ever changes. It's constant, it's predictable, it's easy.
But the real world is all about curves. The path of a baseball, the graph of a company's profits. A curve's steepness is always changing. It might be flat one moment and super steep the next. There's no single slope that works for the whole thing. So how in the world do we nail down the slope at one specific instantaneous point?
Well, the first clue to solving this comes from a really clever trick. Instead of trying to find the slope at one point, which seems impossible, we start by picking 2 points on the curve and just drawing a straight line between them. That's called a secant line. Now, its slope isn't the instantaneous change, but it does give us a pretty good average rate of change between those 2 points.
Okay, so here's where the magic really happens. We want to find the slope of that curve, y = x squared, right at that specific point, 1, 1. So check out this table. We start by picking another point kind of far away, over at x = 2. The slope between them? It's 3. Okay, now let's bring that point closer, say to 1.5. The slope drops to 2.5. Getting closer still to 1.1, the slope is now 2.1. And look at this. When we get super close at 1.01, the slope is 2.01. Are you seeing the pattern here? It's like it's homing in on something, right?
Our approximation is just getting better and better and better. The closer and closer those 2 points get to each other, the more the slope of that secant line seems to be aiming for one specific number. It's getting ridiculously close to, well, it sure looks a lot like the number 2.
And that's it. That's the solution. That line that our secant lines are getting closer and closer to becoming is the tangent line. Its slope isn't an average anymore. It's the exact instantaneous rate of change at that one single point. And calculus gives this incredible number a special name, the derivative.
A great way to think about this is driving a car. Your average speed over a whole trip, that's like the slope of the secant line. But the number you see on your speedometer at any given second, that's your instantaneous speed. That's the derivative. That's the rate of change happening right now.
Okay, so we've cracked the code on measuring instantaneous change. Awesome. Now, let's switch gears and tackle that second massive puzzle, the area problem. This is all about finding the size of shapes that just don't play by the normal rules. We all learned how to find the area of a square or a circle in school. Easy enough. But what about a shape like this? One of its sides is a wiggly curve. You can't just do length times width. So how on earth do you find its exact area? And guess what? The solution starts with another clever approximation. We can't measure the curvy thing directly, but we are really good at measuring rectangles. So the big idea is to slice up the area under the curve into a bunch of skinny rectangles. We find the area of each one, add them all up, and we get a rough estimate. It's not perfect. You can see the little bits that stick out or get messed, but if you want a better guess, you just use more rectangles and you make them skinny. Now here's the leap of genius. Imagine making those rectangles narrower and narrower and narrower until they are infinitely thin. What happens? All those little errors, those gaps and overlaps, they just shrink away into nothing. And the total sum of the areas of all those infinite tiny rectangles perfectly matches the one, true, exact area under that curve.
So, did you catch the parallel there? In both problems, we made a rough guess, an approximation, and then we imagined pushing that approximation to its absolute extreme. That shared idea is the real hero of calculus. It's a concept called the limit.
And it's not just a neat trick, it's everything. As the source material says, the idea of a limit is totally central to all of calculus. It is the fundamental engine that makes the whole thing work. So, what is a limit? Let's skip this super formal math definition for a minute. Intuitively, a limit is just the value that a calculation is getting closer and closer to as you get your input closer and closer to some target number. It was the number 2 that our slopes were aiming for. It's the perfect, final area that our rectangles were adding up to. It's the destination.
And this right here is the big reveal, the beautiful aha moment. The tangent problem? We solved it by finding the limit of the slopes as the points got infinitely close. The area problem? Solved by finding the limit of the sum of the rectangles as their width shrank to 0. Two completely different looking problems solved by the exact same powerful idea. Incredible.
So, that's the origin story, the how it was made. But why is this so important today? Because these ideas, which grew out of these seemingly simple puzzles, gave humanity the tools to actually describe, build, and understand our modern world.
I mean, seriously, being able to work with instantaneous change in areas under curves is the language of physics, engineering, economics, even medicine. We use calculus to plot the course for a Mars rover, to model how a drug moves through the body, to design a skyscraper that won't fall down. The list just goes on and on.
And it doesn't even stop there. You can take these exact same concepts, derivatives and integrals, and expand them into 3 dimensions, or even more. That's called multivariable calculus, and it lets us tackle even bigger problems, like calculating the volume of some complex 3D shape or modeling the weather.
When you boil it all down, calculus is just this incredibly powerful tool for solving problems. It was invented to understand motion and to measure space. Since then, we've used it to solve problems its creators couldn't have possibly imagined. And that leaves us with a really exciting question to think about. What are the next huge challenges that this amazing story, this story of 2 problems and 1 big idea, is going to help us solve?